Okay, hello everyone. Thank you for coming to today's talk at CBCS. My name's Tom and I'm a postdoc here. I'll do a quick short introduction to the speakers and then let them get on with it. So today's talk is on how to engage land managers and decision makers in implementing climate adaptive conservation portfolios. And giving today's talk is Dr. Earl Saxon, who has a wealth of knowledge in the climate change sphere. He was the chief scientist at the AWT and Australian Wet Tropics. Sorry, that's an acronym I know. But more recently is looking to reduce Anthropocene impact on tropical forests. And then Professor Hugh Possingham is going to give a quick talk at the beginning. And everyone knows who he is, but briefly, he was Queensland's chief scientist, but is currently the chief counsellor of the Biodiversity Council and chief scientist at the Nature Conservancy. I'll now pass it over to Hugh to do some more introductions and do his talk.
Thanks, Tom. Thanks a lot. Yes, I resigned from the Nature Conservancy 2 years ago. So I'm chief scientist of Accounting for Nature, which is maybe another talk about what is Accounting for Nature and what do they do. It's a company that verifies environmental accounts. But let me begin by acknowledging the traditional owners of where we are, which is the Yagara and Turrbal people. In general, I won't say too much. I just want to talk a bit about the 30 by 2030 goals. So everybody hopefully remembers there was a meeting in Montreal and all the countries in the world agreed to protect 30% by 2030, right? So that's big. And we were meant to protect, 17% by 2020. And some countries thought they got there. Some countries thought they didn't get there. Australia sort of got there, but didn't really get there in terms of representation. We can focus on the 30 by 2030, but there's more, it's more than 30 by 2030. And I would encourage you to read the whole full paragraph. And the whole full paragraph of that commitment to 30% by 2030 talks about representation. And how many papers has this group written on representation? Probably 200. Don't forget how important representation is. Really, all the ideas about not just having big protected areas, all the early theory in conservation biology was about shape and replication. But in the mid-70s and early 80s, Australian scientists, Jamie Kirkpatrick, who knows Jamie Kirkpatrick? Right. Invented representation and minimum set algorithms. You should know this globally, right? This is the person who first said when they build protected area systems, it's just not the size and the shape and the connectivity, it's how well you represent all the ecosystem types. And that's what underpins Marxan and zonation and all the software. It's getting a bit of everything, It's what underpinned the rezoning of Moreton Bay, which we were involved in. It underpinned the rezoning of the Great Barrier Reef. It underpins almost every single protected area that's done properly in the planet. About half the countries in the world don't do it properly. Don't forget about it. Connectivity is also important. It's also mentioned in the CBD requirements. What's not mentioned is anything about climate change and climate change refugia. There's a big nod to Indigenous peoples and community conservation and traditional owners and sustainable use, and also other area-based conservation measures. What's another area-based conservation measure? OECM. Other environmental area-based. It's the stupidest acronym in the world. But I would also urge you to find out what that means, OECMs, because the 30% isn't all going to be standard protected areas. It can be, for example, sustainably used, possibly forestry. It could involve some grazing land, as long as the biodiversity and carbon and all those other things are being increased. So we're moving from a world which is all about 17% national parks to 30% in some tenure where biodiversity conservation is a primary objective. Got that? And that could be Indigenous protected areas, but it could also include some level of logging. It could include possibly some level of grazing. So that's why we need to keep moving with this, and we need to influence governments to do that well. What's not discussed on most of those things is the issue of climate change. And so clearly, and I don't even think this goal mentions resilience. The resilience of a protected area network is absolutely critical. I think it used to be in the 17% goal, but it's been taken out. What is resilience? That's resilience to change. And climate change is probably going to be the biggest change that these protected areas are going to have to deal with. So that's what Earl's going to talk about. And how do you get that in? How do you get that in to a protected area approach? Again, this group, how many papers have we written on climate change and protected area expansion and management and acquisition? 25. So Anthony's group, a whole heap of other people. So we, again, are world leading in the space. First paper came out on, I think it was Lee Hanna in about 1987, wrote the first paper about climate change, believe it or not, and protected area expansion. So it's not that new a topic, but how many governments do you think have used information about climate change in their protected area expansion? I can't think really of any yet, hardly at all. And maybe somebody online could think of them. So I suppose that is the challenge, and that's why we're doing the work. And the only other thing I'd say is maybe it's an interesting topic for another discussion. How do you actually get governments and big NGOs to pay any attention to proper spatial planning? So that's an open question. Now routinely they use software like Mark's and Zonation. Probably 2/3 to 3/4 of the protected area systems in the world involve some form of systematic conservation planning. The big NGOs use that software that we've all developed, but they're using a version that's probably 15 years old, that often doesn't account for connectivity, doesn't account for costs very well, and certainly doesn't account for climate change, refugia, and other impacts. So they're using stuff, and basically that's the rule of thumb. And what a government does, the batteries can disappear. So we have multiple dramas now. What the government does, broadly speaking, is usually around about 10 to 15 years behind what our papers tell them to do. How can we fix that up? We need to actually just work more closely with them. So that's another of our general tasks. They don't read the literature because they don't have any time. So you actually have to do work with the governments and the NGOs to pay attention to those issues. And so maybe that is another topic for another day, is the successes and failures of getting government agencies and not-for-profits to use the most recent science in spatial planning, which is, we all have opinions on. But the bottom line is you have to keep turning up. Anyway, Earl wants to talk about, this big issue, which is, as I say, even though we've got papers going back 10 or 15 years about taking climate change issues, papers in Spain, papers in Japan, marine, terrestrial, about how climate change can be accommodated in a spatial reservation plan. As far as I tell, nobody use it. So the question is why, and also what are we doing wrong, and what are the easiest ways to put it into the spatial plans? Earl, take it away.
Thank you, Hugh, for coping with all the technical difficulties, as well as being an opinion leader in our field. The notes, which I now cannot see, were intended to make sure I didn't digress from a topic that interests me greatly. So without that protection, there is some risk of digression, but I will try to walk you through what was meant to be a coherent and logical presentation. Beginning with acknowledgements. I think it's Newton that said, if I've seen further, it's because I've stood on the shoulders of giants. And I want to acknowledge the indigenous communities of the world's rainforests and the wisdom that they have preserved and shared. My mentors and teachers, Jeff Tracy, Peter Stanton, my current colleagues who've done the hard work of leading our two papers so far, Paul Elson and Blake Simmons, and Hugh, in particular, his open door policy on visiting scholars and researchers, which has sometimes been a more open door than senior administrators of the university have been comfortable with, but he has managed to push me through that door since 2016. I've always liked the analogy of the work that I do with the task that Noah had. So I was particularly fond of a comment I read just a couple of weeks ago. This time we're going to need a bigger ark. The parallel is that neither Noah nor today's conservation planners knew how long the Ark was going to have to protect the biodiversity that was in it. In neither case was the Ark or our conservation areas intended to be the perpetual and enduring habitat of fauna, but only a temporary measure. Since you and I don't have the expert advisor that Noah had, we have to use the best scientific advice, but also exercise a certain amount of risk management. And therefore, I'm posing the question as to whether a 30% goal would be filled, if you like, or prioritized differently if you're anticipating the impacts of climate change than if you're not. So we start with a couple of premises, which you can question if you want, but then you'll have to give that talk. I'm going to stick with these assumptions. And one is that the places which are currently suffering limited human impact, have intact land cover, if you like, are the primary candidates for successful conservation outcomes. There's nothing novel in that. And the other is that we can't predict reliably enough where all these ecosystems will move and how they will adapt. And therefore, the most stable places, the places where climate will change least, should be our second criteria for building Anthropocene refugia. Now, for those who are technically minded, these are 4 scenarios for the pace and severity of climate change. The 2 top ones are what are called asymptotic, that impacts of climate change, changing global mean temperature increases to the end of the century and doesn't level off until sometime later. And these were characteristic trajectories for all the modeling that was done up until about 2010, not because anybody thought the world could actually be managed that way, but because that was the best that computers could handle. The limited ability of computers to work through all the pixels and voxels meant that these scenarios without feedback, in other words, climate change increases, nobody notices, nobody does anything about it, were the trajectories that people worked with. In 2007, I had the good fortune to work with a ginger group advising IPCC on which scenarios to use in coming decades, what were coming decades in 2007. And we successfully advocated the 2 lower scenarios. Both of them peak and decline. We assumed that there would be a human response to climate change that would reduce the pace and severity of climate change. And one of them exceeds the 2-degree threshold temporarily, and one of them doesn't. Having explained all that to you, I'll now argue that we not only don't know which of these 4 scenarios accurately reflects the future, but for the purpose of building our Anthropocene refugia, it doesn't really matter. So the answer with peak and decline scenarios is actually very simple, because some places will retain the habitat conditions that they presently have moving into the future. So that's your easy, low-hanging fruit. The challenge is in the extreme scenarios where current habitats literally disappear, totally new habitats occur. And I would argue that in those situations, it's the source populations, the places where plants and animals will persist for the longest possible time and then successfully disperse, that have to be the priorities for conservation. Now, as it happens, we did an early run using Marxan in 2008, and in many places in the tropics, the current whereabouts and the future whereabouts, or as one of my colleagues calls it, the whenabouts of current bioclimatic conditions overlap. So in this study, we found that only the blue spots would be taken out of a portfolio that looks at current and future conditions. And the red spots are ones that wouldn't be included in a current only portfolio, but need to be added to make sure you have the future whereabouts of particular habitats. And is Carissa here? Yes, there. The author of this study, which shows the opposite situation where the current and future habitats of Australian fauna largely do not overlap, and where it would be very hard to set up a portfolio where you said we're going to have all the current habitats, all the future habitats, all the stepstone habitats in between, and we know how those community dynamics will operate and when. So possibly if there's a 60% goal, we could do that, but under a 30% goal, I don't think we can. In terms of a Venn diagram, the left-hand picture is the happy situation where current habitat in blue overlaps with future habitat in red, and a good chunk of that is already in a protected area. And the extension of existing protected areas that one recommends is the yellow patch above where they all overlap. In the second case, where the current and future whereabouts do not overlap, I believe it is possible to identify the places which change least. And that's the innovative bit that my colleagues and I have done, and that I want to invite you to continue to participate in. Now, there are lots of bioclimatic organizations of data. The one we've used is Holdridge Life Zones, originally built in 1947, based on Holdridge's awareness of Central American tropical forests, but extended into a global system. And it uses 3 parameters: precipitation, biotemperature, and an aridity ratio to define hexagonal spaces. As marks and aficionados, you'll enjoy. I don't have to argue the benefits of hexagonal spaces with lots of neighbors. What we found when we applied this to real world data and the climate change projections is a whole host of new Holdridge life zones. In other words, there's more variety in the real world than Holdridge originally imagined or described. Our new ones are above and to the right of the black and white dotted line there. Now to move a little bit into mathematical space, the 3 dimensions of the Holdridge system are not orthogonal. In other words, in the real world, there's a relationship between temperature and precipitation, and a relationship between precipitation and aridity. This is not new to you ecologists, but as it happens, the trapezoidal shape that you saw previously fits in more or less as a slab in this 3-dimensional space. And the bounds, the max and min bounds, were set by Holdridge in terms of where he thought life could exist on the planet. And the trapezoid has 4 corners, each of which is an extreme of hot and cold. Now, given that the vectors are not orthogonal, if you want to look at displacement in Holdridge space, you have to start with a principal component analysis so that you're measuring current and future combinations of these parameters, but it's not an abstract PCA space. The principal components in Holdridge space actually correspond to things that we know and love in biogeographic studies, such as latitude, moisture stress, and above ground biomass. So although there's a fancy mathematical model going on here, the parameters are ones you can describe in almost any landscape. Not surprisingly, climate change has directionality. The changes between current and future climate or current and future position in Holdridge life zone space are not random, they're not stochastic, they are powered by the greenhouse effect, so that the predominant direction of change, the most frequently found change, it gets warmer. Hence, global warming. Again, not rocket science. The second direction is that it more often gets wetter than drier. And again, this follows the physics of if it's going to be warmer and there's going to be more evaporation, it's got to come down somewhere. But it doesn't come down equally everywhere. So some places get much wetter and some places actually end up being drier. Again, not rocket science, and we're trying to reflect in our modeling patterns that people who actually deal with individual ecosystems will be familiar with. So here's our first finding. Yeah, the colors on the circles show the relative proportion of outcomes. The top right map shows the changes which have been detected or which we've modeled based on historical and contemporary global, global climate data. So even in the period, the century from 1910 to 2010, there has been some increase. Blue is wetter, orange is warmer, and some of those other combinations. And then if you go down to the bottom, using a strong scenario, the maximum scenario I showed before, you still have 50 or 60% black, meaning areas that do not move from one Holdridge life zone to another. They may well shift within a Holdridge life zone. And if you can picture where we were before with the hexagons, it's possible to move a fair way across a hexagon if you started from one side and you don't get to the other, whereas if you start very near a boundary, you can trip over into the next hexagon with a very small displacement in Holdridge life zone space. So one of the research questions, which Salit and I have batted back and forth now for more than 3 years, is the reality of the Holdridge boundaries. For this first study, we accepted that Holdridge boundaries are real. And if you move from wet tropical forest to hyper wet tropical forest, you'd actually notice this on the ground. For the next stage of our work, I'm proposing that we'll treat all displacements equally. In other words, any displacement in the three principal component analyses will be regarded as comparable, whether that takes you across within a Holdridge life zone or takes you across an ecotone. But that's a topic for research. Thanks to Blake Simmons, we've put together our two parameters, life zone stability, and human footprint. And we have this for the planet for two different future scenarios at two different times at 1 kilometer resolution. looking at it globally, it's clear that the cold temperate world is predominated by unstable but intact landscapes. That's the red color. The temperate and the subtropical world is largely stable climate and modified, light blue, or unstable and modified pink. When we get into the tropical world, it's not such an easy or uniform story. And Blake has compiled this amazing chart with, actually, I don't have the count, somewhere over 175 countries or territories. We always argue back and forth about Greenland. And the black ring there is the 30% threshold. So Australia, I'm not sure Australia, if they can see that in the video version. Australia, point to for those who are in the room, is just to the right of the upper middle. There's a label at the top. I don't know whether the whole screen can be seen. I don't know whether the whole screen can be seen online. Can it?
It's too small to read.
Oh. Well, I put Australia at the top because that's where Australia belongs. And you can see that there's relatively few countries where 30% or more is in dark blue, which means they have more than 30% of the country is both unmodified, that is low human footprint, and stable. So at one level, terrific, job's done. Now we can move on to some other country and their problems. By the way, in Europe, which is the top left side here, Greenland is the only country or territory that meets that qualification. However, when we look more locally, the conditions can be more challenging. This is northeast Queensland, the footprint of the wet tropics. And it turns out that only the highest parts of the mountains stay in the same Holdridge life zone. So even though there's a large area that's relatively intact, or at least, excuse me, at least not getting worse, from a climate point of view, climate may be a bigger threat to its biodiversity than other forms of human disturbance. I'm now going to go relatively quickly through a couple of data sets relating to the tropical forest ecoregions of Indo-Malaya and Austronesia, which Hugh and I have tossed around as being potential study sites or platforms to see whether a climate adaptive portfolio would be different from your ordinary, the last 300 papers that have been prepared on this topic. I like this slide for two reasons. One is it gives you this idealized version of where the tropical forest ecoregions of the world are. This, if you like, is a people-free version. And then I've put in the corner the Wallacea and its various definitions. If we didn't have impacts of people, either on the ground or climate change, this is the world as it might have been. In the real world, however, let's look at 4 examples. This is Tanantai province in the southeast corner of Burma or Myanmar. It is the largest remaining block of tropical forest in all of Asia, or for that matter, Eurasia, and it's not all that big. Here are land systems of Borneo or Kalimantan, the Indonesian part of Borneo. And this has been, shall we say, worked over, chewed over. There's probably a whole library of conservation strategies for the heart of Borneo, and even soft plush toys have been sold to people who contribute to conservation outcomes. But I think it would be fair to say that none of these strategies have kept pace with human activities, logging, plantation, or mines, and certainly none of them have anticipated the impacts of climate change. So this is an area where a climate adaptive portfolio might not be different because there's so little to work with. But to the extent that it is different, they would be really important things to add.
We're running out of discussion time.
Okay, I'll speed through the rest of it. Another example, the island of New Guinea, which is part of two different countries and actually has in some ways different ecosystems in different parts because the island is being pushed north by plate tectonics. It has swampy ecosystems in the southwest and volcanic ecosystems in the northeast. So a conservation portfolio has to take a whole of island approach. I think I can skip over the Paluma Range, which everybody knows. I'll just briefly show you the distribution of above ground biomass that reflects not only where the intact forests are, but now that we have recognized the role of forests in carbon capture and storage, there's arguments for using above ground biomass as a target itself. Here's a closer look at the four patches we've talked about. You can see the relative size of which North Queensland is the smallest. We actually do have very good data on land management in each of these places. In some cases, like Central Kalimantan, the international community has more reliable data than the agencies who are managing those resources on the ground. And then just to end on a happy note, the fragmented land tenures of the Paluma Range in wet tropics that characterized the region when wet tropics was created have fortunately been superseded as forestry tenures got moved into the national park and native land title. Management responsibility came under a single authority, but the management problems of this interface between tall eucalypt and wet tropical forests has not gone away. So leaving you to remember all those current issues in all of those places, the point of this last slide is that the distribution of magnitude of future climate change is not correlated with any of those patterns that we have been focused on. If you look at Central Kalimantan, it's about mid-range in magnitude of climate change between the least and the most in this chart, whereas other areas like the eastern mountains of New Guinea are down at the low end. So I'm pretty confident that taking climate change into account is not going to result in the same changes to portfolios everywhere. It will become more critical in places where climate change will be greatest. And I invite you to participate in finding those places. To summarize our research questions, one is the extent to which the human footprint should continue to be used as our index of human pressure on the landscape, or whether we can actually just use above ground biomass as a more reliable indicator of the viability of our targets. Second question I alluded to earlier is whether the Holdridge life zone boundaries are real and therefore a displacement in climate space that traverses the Holdridge boundary is a more significant impact on the biota, excuse me, than a displacement within Holdridge life zone unit itself. And last but not least, the task of comparing two portfolios.